Okay, hello everyone. Back again with another video, still on data visualization. This is one of the last ones I'm going to do on data visualization. And today in this video, what I'm going to do is demonstrate how to create ECDF plots using seaborn. So the ECDF plot, ECDF stands for Empirical Cumulative Distribution Function. And these are really useful plots for visualizing the distribution of variables. And they basically show the proportion of the total data set that is accounted for by given values on whatever scale your variable is measured, sorted from lowest to highest. Okay, they're particularly useful when comparing the distribution of scores between groups and categories. There are a number of benefits. We can use them to compare groups. We can see the frequency or the proportion of a given score that accounts for observations in the data set. But there are some disadvantages. They're not the best way to visualize data if you're interested in showing what the central tendency is, or if you've got some sort of bimodal distribution. Anyway, so I have in other videos already created some ECDF plots just as examples of the types of plots you can create using seaborn. But to this video, I particularly like these empirical cumulative distribution function plots. I'm starting to prefer them as a way to create visualizations where you've got multiple groups, so you can see if there's a difference between the groups in scores of some sort. Okay, so to start with, as ever, I'm using Jupyter Notebook. I'm working in Python, so I'm going to import some software libraries that may be useful in this video. So I'm going to import pandas as PD. I'm going to import NumPy as NP. I'm going to import matplotlib.pyplot as PLT and seaborn as SNS. So using the conventional nicknames that we or abbreviations that we give to those software libraries. To start off with, though, I'm going to basically just make up some a short list of data to demonstrate kind of how the ECDF plot works. So what I've done is create this object here, called it vals, short for values, and I've given it a Python list containing these square brackets. There's only 10 data points, and they're sorted in order from lowest to highest. So I've got 1, 2, 2.5, 2.5, 3, 5, 6.5, 6.5, 6.5, 8. So the minimum value is 1, the maximum value is 8. And I'm going to create an ECDF plot of this short set of 10 data points. So if I run that cell using the sns.ecdf plot method, and I've passed, as the x variable, I've passed vals as the argument for that. So what you can see here is the x-axis runs from 1 to 8, so the minimum, it runs between the minimum and maximum value on the scale, whatever scale the x variable is being measured. And on the y-axis we've got proportions, so proportion of the total data set that's accounted for by a given score. So we've got 10 data points, so each one of these represents 10% of the data. So we've got 1, 1, and you can see here we've got this line at 1 that goes up to about 0.1. So it's showing that 1 represents 10% of the data. The next data point is 2, so if we move horizontally across to 2, we've also got 1, 2, so that represents 10% of the data. So we've got the line then goes up to 0.2. So this 2 represents 10% of the data, the 1 represents 10% of the data. In combination, by the time we've cumulatively accounted for both of theirs, we've accounted for 20% of the values in the data set. And the height of these vertical lines is an indicator of of the proportion of the data set when we've got multiple scores. So you can see here we've got 2.5 and another 2.5. So 20% of the data there is represented by the score 2.5. And if we look at where 2.5 would be on the x-axis, we can see this this longer vertical line, in that accounts for, it goes from 0.2 to 0.4. So it accounts for about 20% of the data. Let's look at one more. So 6.5, we've got three 6.5s, and if we look at that, we can see that accounts for 30% of the data. It goes from like 0.6 to about 0.9. And what we can do, the useful thing about these kind of ECDF plots, these cumulative distribution function plots, is we can look at for a certain value the proportion of scores that fall below that value. So if we took 5 here, we could see that 5 is, if we log 1, 2, 3, 4, it's like the 6th data point in our data set. We can see that from 5 here, that 60% of the data is has the value 5 or lower. Conversely, we can look the other way, so that would leave us the remaining 40% of the data has a value of greater than 5. Okay, so this looks quite jagged. It's like large steps because we've only got 10 data points. The more data points you have, the more smoothed out that cumulative density function will look. So here I'm just creating another variable, and I'm using a random number generator. I'm using the numpy np.random.randint. So it's going to generate random integers between 0 and 10, and I've asked it to generate 30 in total. So it's a bigger data set than the previous one, and if I run that, you can see it's kind of it's quite jagged and stepped, but it's much smoother than the one above in terms of like large jumps. There are fewer large jumps, essentially. Okay, so let's look at I'll import some data, and we can look at some ECDF plots from real data sets. Okay, so to start with, I'm going to import the tips data set that I've used in previous videos. It's one that's available kind of open source online. I think it's data that relates to tips to some server in a restaurant, maybe in New York, somewhere like that. And I'm going to use the pd.read_CSV method. I've got it saved as a CSV file on the computer. I'm going to save it as an object called df for data frame. If I run that and we look at the head, you can see we've got a number of variables, some measured on scales, some are categorical. So total bill, tip, things like that. And what I'm going to do is I'm going to create an ECDF plot for tip. So the tip values that servers have been left by different groups, different customers. Note, as I said above, that the x-axis scale will run between the minimum and maximum value for the variable, and I think for this particular variable tip, it kind of ranges from between like $1 and $10 or something like that. It's not like a hugely lengthy scale. And they are decimals, so the values vary, but if you have a particularly large scale which is continuous and is measured quite precisely to a number of decimal places, it will often look quite messy on the x-axis when you create your ECDF plot. It'll look quite crowded, essentially. So these plots are often they're often better for visualizing data that's recorded on a more discrete scale. Let me run this and we can see here. So say the same as above. So what we're seeing here is tip is, as I said, it runs between $1 and $10 essentially, and we can see the proportion of tips are accounted for by certain values in order from lowest to highest. And as I said before, those kind of vertical jumps in the plot represent multiple data points for that particular value. So if we look at $2 here, it goes all the way, it goes from 0.2 to nearly 0.4. So it's probably maybe about 15% of the data is represented by $2 tips. And we've got another kind of jump here. So this is maybe $3, I think. It goes from about 0.5 to 0.6, so maybe 10% of all tips were of about $3 in value. Okay, let's look at some other Let's look at some other data. So I'm going to import a data set. I'm going to call it, I've created an object called variables, and I'm just going to import the variables that I'm interested in. So this is results data for certain postgraduate programs and the grade that people got on a particular course on that program. So if I run this, what you can see here is we've got a small data frame. We've got a categorical variable for program, and then we've got grade, so like a percentage grade, and we'll create an ECDF plot for that. What I should point out, because we'll see a difference, I guess, with this plot and the one above, is this particular plot for the tips data. This is quite a large data set, so it looks a lot smoother. I think there are a few hundred data points in that. I'll convert proportion to count later and show you how to do that, and then you'll be able to we'll be able to see exactly how many data points there are. So as I said, the more data points you have, the smoother the ECDF plot will appear. So this data set, which is this results data frame object that I've created here, has about 62, 63 data points in it, and that's kind of produced a much smoother cumulative distribution function than the ones we saw above, where we just had 10 data points or 30. So we can, as I said, one of the useful things about this is we can use ECDF to evaluate the proportion of values or scores below, above, or between 2 points. So this is similar to what we do with a probability density function, but when it is presented visually as an ECDF, it's actually easier for us to interpret in some ways, because we can just kind of read off the proportion. Usually, you know, if we create a probability density function, whatever shape of the distribution is, we then have to look at the 2 points between which we're interested in. It might be any score below kind of 50 or something like that, and then we'd have to maybe do some sort of calculation to work out the proportion that actually falls below 50. On the cumulative version of that, which is what we're looking at, we can just kind of read the proportion off the y-axis. So what I'm going to do here is I've just added an extra line to this plot. I'm going to create the plot above again, where we've just got grade on the x-axis, but I'm going to put like this vertical line at grade 70. So if I run that, so I've created this black vertical line here at grade 70, and what we could do is look at this and then read off from it, and what we're seeing is probably about 0.5 or 50% of 50% of the data falls below the grade of 70. So conversely, the complement of that 50% would fall above it. So we can use this to visually just work things like that out. So if we look 0.5, we could say 50% of data points have a score of 70 or lower, or 50% of the data, the other 50% had a score of 70 or higher. Okay, so we can actually flip this axis though, so we could kind of flip the axis and put grade on the y-axis and proportion on the x-axis. So I'm going to do that, and I'm going to also plot this just to sort of confirm what we thought here. I'm going to plot this vertical line again, but I've had to change it slightly because the scale on the x-axis will change to between 0 and 1. I'm going to plot it at 0.5, so at the 50th kind of percentile, and you see there it's basically like the above plot has been mirrored across this diagonal here. The black line is now at 50%, and if we kind of read off from that, we can see that what grade does that relate to? It relates to a grade of roughly about 70%. Okay, and we can confirm that. So the 50th percentile would be the median grade. So we could confirm that just with a quick calculation using NumPy and pandas, and by basically just asking for calling the data frame, calling the grade variable, and using this median method. And what we see is, so 68, the y-axis score here is actually 68, so close to 70. But that's what I like about these plots, is it kind of makes it easy for us to interpret proportions by just eyeballing the plot. Okay, so as with many other plots in Seaborn, it's a really easy way to compare groups. And I've demonstrated with other types of plot that we can use the hue argument to compare groups on a particular variable. So on looking at the results data, we had a number. This program is a categorical variable. It relates to a number of different postgraduate programs that people might take, and we can specify that as being the hue. So it will create different lines for each of those groups that are in different colors. So we can see here, the blue line relates to PTI, the red line relates to cog neuro. So you can see here differences. You get some where we've got five different groups plotted on here, so it gets a bit crowded, but you can see where the differences between the groups are. Certainly at this kind of lower end, there's a big difference in scores between certain courses with some. So cognitive neuro scores are generally higher than some of the other courses. Okay, so let's look at another example. So using the hue categorical argument is kind of really useful when you have a number of groups like this, but that plot looks kind of rather busy and crowded. So here's just another example from the tips dataset. We're looking here at, I've just used sex, which was a categorical variable in that dataset, as the grouping variable for hue, and we can see here is the blue line represents females, the yellowish line represents males, and if we look at that in terms of were males or females better tippers, there's not a great deal of difference. There's a lot of overlap, but when you get to the kind of higher end of tipping, there seems to be a large portion of males giving higher tips up here. So a plot like this comparing two groups much easier to see and interpret than this one above. Okay, so far everything we've looked at has presented the proportions of our data, but we can actually change that by using this stat argument. And I'm going to create the plot for the grade data. I'm taking the hue argument out, so we're just looking at the single plot. And rather than presenting proportion on the y-axis, I'm going to present count. And there you see, it gives us the same plot, but rather than seeing proportions, we're seeing the actual count of data. And as I said, there are either 62 or 63 data points in this data set, so that the top of the y limit now is about just above 60. Okay. If we look at tip as well, we can change that from proportion to count, and then it gives us an indication there. So as I said, a much bigger data set, and this scale seems to go up to about 300. So 300 observations in that data set. But there might be a reason we'd want to kind of know, what does 10% of the data or 20% of the data relate to? And we can see from looking at that, it kind of probably relates to about 30 observations, something like that. Okay. Now we can do a similar sort of thing. We could add the hue argument back in. The interesting thing that this is going to do, though, is where this was shown as proportion up here. Each of the lines we got a cumulative score for each group, and it has to run from 0 and sum to 1 essentially. But these different courses may have different number of students on them, so there may be a different number of observations in each group. And if we change our stat to count from proportion, we will see those differences. Okay, so if we look now, then we can see in terms of counts, we can see that obviously, so the PTI group had kind of way more. Let's go, probably got about 20 something students. Flynn Psych had above that, probably about 22 students. There were only about 8 students looking at this, 8 or 9 students on the cognitive, and similar for maybe about 6 for the developmental. So it presents the differences so that the data looks different here, because there are different numbers of observations in the groups that we're comparing. So the last thing I'm going to demonstrate here is it's created a legend on this plot for us, and it's used the default. As a default, it's used the way the name is saved within the actual data frame. So if we go and look at data frame, you can see it's kind of saved with underscores and it's all lowercase and stuff like that. But we might want to tidy that up. We might want to change that legend so it looks neater for publication reasons or something like that. And the way we can do that is we can save this actual plot as an object. I've saved it as EPL, so ECDF plot. It's just an abbreviation I've come up with there. I've saved it as an object called EPL, and I've changed it. I've changed from count back to the proportion, and then I'm using. Once it's saved as an object, it returns a MATLAB axis subplot object, so we can then use any of the kind of MATLAB styling options that we could for any kind of matplotlib styling options. So I'm going to call the object EPL, and then I'm going to use the .legend method. And what I've done is, in the order I want them to appear, I've just passed the way I would like each of the program names to appear. And you should see now that it's removed the title. It said program above it. We could add a title back in, but you can now see as I've specified them there is how they appear on the legend for that particular plot. Okay, and like I said, if there are lots and lots of styling options you can use with Seaborn, and it is kind of built on. It's built on the matplotlib software library, and if I use this type function and I put our EPL object into it in a minute, then you can see that it's kind of a matplotlib axis subplot. So any of the kind of styling you can do in terms of line width and things like that, and titles and things you can do on a plot like this. Okay, so lots of other. I've only demonstrated some of the options here. I like ECDF plots. I'm finding that they're often a better way to look at how the distribution of two variables is, or multiple variables is presented, and as ever, there are lots and lots of things you can do, and I would recommend you check out the matplotlib and the Seaborn documentation online to see all the different parameters and arguments you can use. I've just demonstrated a few very simple ones to sort of show how to create these plots and maybe change some of the formatting, but there are a lot of other things you can do. Okay, thanks for listening.